Today we're going to do section 8.3, relative rates of growth. Question, if I gave you two functions and asked you which one grew faster and which one grew slower, or if they grew at the same rate, how would you decide? First, let f of x and g of x be positive for x sufficiently large. 1, f grows faster than g, and g grows slower than f as x approaches infinity if the limit as n approaches infinity of f of x over g of x equals infinity, or equivalently, the limit as n approaches infinity of g of x over f of x equals 0. 2, f and g grow at the same rate as x approaches infinity if the limit as n approaches infinity of f of x over g of x equals L, and L does not equal 0. Let's look at this example. Which grows faster, y equals x or y equals 2x? So we would take the limit as x approaches infinity of 2x over x. So here, 2x is acting like f of x, and x is acting like gx. So this is equivalent to the limit as x approaches infinity of 2, which equals 2. So y equals x and y equals 2x grow at the same rate. Because the limit as x approaches infinity of 2x over x is L. It is some number and it does not equal 0. Let's look at example 1. Compare an e to the x and x cubed as x approaches infinity. Show that the function e to the x grows faster than x cubed as x approaches infinity. So we're going to have e to the x be f of x, and x cubed be g of x. So the limit as x approaches infinity of e to the x over x cubed. And here, if I went to infinity, I would get 0. I'd get infinity over infinity. So we need to use L'Hopital's rule until we can come up with an answer. So then I would have the limit as x approaches infinity of e to the x over 3x squared. Again, I'd get infinity over infinity. And I get e to the x over 6x. Take the derivative again. And I get e to the x over 6. And that would give me positive infinity because it would be infinity over a constant. So since I got infinity, I just showed that f of x, my e to the x, grows faster than x cubed. So we must justify using limits, and I just did using the rule. Does this suggest a rule to you? And you should be thinking it does. And the rule is exponentials grow faster than polynomials. Let's look at example 2. Comparing the natural log of x and x as x approaches infinity. Show that the function the natural log of x grows slower than x as x approaches infinity. So the limit as x approaches infinity of the natural log of x over x. Again, we need to use L'Hopital rule. And I'd get 1 over x divided by 1. So this would be the limit as x approaches infinity of 1 over x, which equals 0. So I just showed that the natural log of x grows slower than x, not faster than x cubed. So that should say grows slower than x. Would it matter if the base changed? No, it would not matter. Also, does this suggest a rule to you? And the rule is logs grow slower than polynomials. So again, this should be just x. Example 3. Compare an x and x plus sine x as x approaches infinity. Show that the function x grows faster grows at the same rate as x plus sine x as x approaches infinity. Does this suggest a rule to you? So again, we're going to take our limit as x approaches infinity of x plus sine x all over x. And this would be the same as the limit as x approaches infinity of x over x plus the limit as x approaches infinity of sine x over x. This would equal the limit as x approaches infinity of 1 plus the limit as x approaches infinity of sine x over x. And this would equal 1 plus 0, which equals 1. So since I got 1, which is L, a number, they grow at the same rate. And adding sine x in the numerator is like adding another constant in the numerator. Example 4. Show that the function f of x equals the square root of x squared plus 4 and g of x equals 2 minus the 2 square root of x minus 1 all squared grow at the same rate. So here, the limit as x approaches infinity of the square root of x squared plus 4 all over 2 square root of x minus 1 squared. So this plus 4 and this minus 1 just shift the functions left and right. So it would be the same as taking the limit as x approaches infinity of the square root of x squared all over 2 square root of x all squared. So this would become the limit as x approaches infinity of x over 4x, which equals 1/4. So since I got L, a number, it goes to a limit, L, 1/4, they grow at the same rate. And polynomials of the same degree grow at the same rate. Polynomials of a higher degree grow faster. Transitivity of growth rates. If f grows at the same rate as g as x approaches infinity, and g grows at the same rate as h as x approaches infinity, then f grows at the same rate as h as x approaches infinity. Base doesn't matter for the growth of logs. What about exponentials? For example, the limit as x approaches infinity of 3 to the x over 2 to the x equals the limit as x approaches infinity of 3 halves to the x, since they both have an exponent of x, which equals infinity. So the higher the base leads to the higher growth. So higher base leads to higher growth. So as a summarizer, and we'll go over the answers to this in class, put the following functions in order from slowest to fastest growing, based on the rules that we came up with from the video.